Our discussion on digital modulation techniques. If you may recollect, we have been talking about passband digital modulations, and so far we have talked about the digital modulations or passband digital modulations for channels where bandwidth is not a constraint, right? We will now take up digital passband modulations for band limited channels. Okay, so passband modulations for band limited channels. And the best point to start this discussion would be to recollect our baseband modulations for band limited channels. What was the essential feature of baseband modulations for digital band limited channels? If you may recollect, the essential feature is that more or less we are constrained to use either a single pulse shape which lies within, whose bandwidth lies within the channel bandwidth, right, or at best we can have multiple pulse shapes all satisfying the bandwidth constraint. But if you may recollect, we suggested for baseband band limited channel digital modulations essentially some kind of a QAM kind of modulations, right. We suggested constellation diagrams which were points on the real line, right. That is, a pulse of a particular shape which satisfies your required bandwidth constraint or criteria, maybe the Nyquist criteria, is used with multiple amplitudes, right, depending on the number of levels you want, depending on whether you want 4 level or 8 level or 2 level. 2 level of course will become binary, but we are now considering in general memory situations, right. So this is what we did in baseband. We want to generalize this to passband now, and if you recollect, essentially we can have a relationship between baseband and passband through the carrier, through the introduction of a carrier, right, and the further generality we can introduce is that we can have 2 carriers in quadrature instead of 1 carrier, right. In fact, we have discussed this point earlier. So I could have therefore this kind of a constellation independently available on 2 different carriers which are in quadrature, right, and I could combine them into a complex plane rather than on a real line. So essentially the difference between Emery baseband modulations and Emery passband modulations would be that I could define now such constellations on a complex plane with real and imaginary axis rather than essentially on a real axis. So the generalization would be therefore to go from here to here. Okay. For example, if I have a binary modulation on each of the 2 carriers, 2 quadrature carriers, right, I will get a 4-point constellation which now looks like this. If I have a binary modulation on cosine omega naught t and another binary modulation on sine omega naught t, right, maybe this modulation will be governed by the first or even data bits, and this may be governed by the odd data bits. The odd data bits may be modulating this carrier and the even data bits may be modulating this carrier, right, or we are taking a block of 2 bits and one of them is modulating this and the other is modulating this. I mean, this is a very crude way of looking at it, but this is one way of looking at it. Alright. So if one error bit is modulating this and the other error bit is modulating this simultaneously, and both of these modulations are taking place together, then effectively when you sum up these two channels together, we will get a point which is the resultant of this point, and let us say if both are 1, right, the resultant of these two which will be this point. If we are getting a 0 and a 1, the resultant will be this point. If we have on this channel this point and on this channel this point, then the resultant will be this point, right, and so on. So depending on the specific combination of 1s and 0s that we have modulating the two quadrature carriers, we will get one of these 4 resultant vectors or points. They can be represented by one of these 4 points. Is it understood? Very clear? So essentially we can therefore say that passband modulations, band limited passband, Emery passband modulations can be represented by a constellation diagram on a complex plane by specifying a set of points on the complex plane where the real and imaginary components of this can be thought of as quadrature carriers, right. In fact, to start with, to keep our discussion very general, we will not even bring in the concept of this cosine omega naught t and sine omega naught t here. All we will say is that these are 4 points in a complex plane with some real coordinates and some imaginary coordinates. Coordinates, this is the real axis and this is the imaginary axis. Fine. So in general, for a QRE modulation that we had on the real line, right, suppose I had a Q level modulation on the real line alone, I can now define 2 Q level modulations, one along each of these quadrature axes, and therefore I will get an overall constellation which will have how many points? Q square, right, Q along one axis and Q along the other axis. The product of these two will give you the total number of points in the constellation diagram. For example, if you just remember our discussion a couple of minutes ago, if I have a binary level modulation on each of these two carriers, right, I get a 4-point constellation in this complex plane. I had 2 possible points along this axis and 2 possible values along this axis, and therefore the overall number of points that I have in the constellation is 2 into 2. If I had instead Q possibilities along this axis and Q along this axis, I will have an overall number of points which is Q square, right. That will give me some kind of a rectangular constellation. That is, I will show you some of these constellations in a few minutes. So a QRE constellation on real line by this procedure would be mapped into a Q square array constellation on the complex plane, right.
So that would mean you would be transmitting log 2 of 2 bits at a time, log Q.
What, suppose this value is m, right, suppose we define Q square equal to m, so we have an Emery modulation scheme where m is Q square, right. This is our new value of m now. That is why I have defined this to be Q rather than m, right. So if I have a QRE modulation scheme along, this is, mind you, just an example. This is not the only way of defining constellations in the complex plane. This is one possible way, and this possible way of describing will produce for me an Emery constellation in the complex plane, which will be essentially how will they be distributed in the complex plane? What kind of distribution you will see? some kind of a rectangular distribution or a square distribution, right? Just like this one is. This is a square distribution, and that will be a square with larger number of points, essentially q square number of points. But I can have many other kinds of distributions too.
Why is it a square?
Because I have q along this axis and q along this axis, and they are independently modulating the two. This, if I do things in this particular way, there are other ways of doing it, right? If I independently can have q equally spaced points along this axis. Yes. Why don't usually we will not choose q equal to 3, right? We'll choose q itself to be a power of 2, right? So let's take q equal to 4, right? So you could have this, then this, right? Similarly, I could have 4 values here, right? Sorry. Now, depending on what combination of coordinates I have here, I'll have a resultant coordinate here. And how many such resultant coordinates you'll end up having? 16. That is the point that I have, right? And each of them will be obviously distributed in some kind of a fashion like that, right? Sorry, it will be like that, and so on. In fact, I have drawn these constellations for you separately, and I'll show them to you. Yeah. So that's precisely what I said, a square grid, right? When I say distributed in a square shape, essentially I meant that these points can be thought of as lying on a square grid, all right? Like this one is. This is on a square grid with 4 points. This will be on a square grid with 16 points, and so on. In fact, I have got them drawn more neatly here for you. This you can. This is a same 4 constellation system that I have shown earlier, and this is the same 16 level system that I have shown a few minutes ago.
What is QAM?
I'll just talk about it. In general, well, let's first talk about this one. You can think of this as QPSK, right? Because essentially you will see that the 4 signals that you will now have will produce a resultant carrier with same amplitude, right? The only difference which will be there from one point to the other point is the phase, right? And that phase is the angle that you make, let's say, with respect to the real axis, right? So you can think of this as a QPSK or Fourier PSK system, modulation system, right? And similarly, we can think of this as a 16 level system or 16. Now we cannot say that there is no amplitude variation and there is only phase variation, right? You can see as you go from one point to another point, there is possibility of both amplitude as well as phase variation of the carrier. The resultant carrier that you will get after combining the 2 quadrature carriers, the in phase and the quadrature carriers, will have a resultant amplitude and phase which will be different from point to point. So we simply then call these kinds of modulation schemes as quadrature amplitude modulation schemes.
It should be called QPSK.
This one? Yeah, we can call it QPSK, sure. I said QPSK to start with. Fourier PSK or QPSK is the same thing. QPSK stands for quaternary PSK, which is again Fourier PSK, right? These are different ways of describing the same constellation.
That is quaternary or quadrature?
No, this means quaternary. That is 4-phase PSK. Basically, I mean, these are the different ways by which you describe these things.
Suppose it is in quadrature PSK.
There is nothing like quadrature PSK. In general, we talk about quadrature amplitude modulation, right? Quadrature PSK, quaternary PSK is also an example of QAM. It's a special case of QAM in which there is no amplitude fluctuation, right? But in general, such constellations for which the resultant carriers corresponding to different points
If no amplitude
could have different amplitudes and phases are simply known by the name of quadrature amplitude modulations, right? Yes, Varun, what is your question?
If it is no amplitude fluctuation, then how can we call it amplitude modulation? We have
We do have amplitude
in
variation,
this one,
isn't
the
it?
QPSK.
In the QPSK, I'm only saying that this you can regard this as a special case of QAM in which there is no amplitude fluctuation. You did not listen to me completely. This is what I said. Alright? Fine? This is a possibility. Now here are some more possible kind of constellations you can have. Here is another constellation for you. I have again 8 points here now instead of 4. Right? Now this is not produced in the way I described a few minutes ago. The manner in which I suggested when I was talking about these constellations, I said okay, we can think of these as 2 data bits independently modulating the 2 quadrature carriers, right? That is why we were then forced to lie on a square grid, right? Because of the manner in which we are talking about things there. However, there is no necessity to think of a general quadrature amplitude modulation in this particular way, right? You can basically choose any set of points on a complex plane and associate a certain number of bits representing that point, right, to be represented by this point. For example, I could choose 8 points which lie on a circle, right, equally spaced in angle on the circle, and I could represent a sequence of 3 bits by these 8 points, right, depending on the different values of these 3 bits, in which case I'll have an 8-phase PSK or 8-array PSK, because again in this constellation the amplitude remains constant and there is only a phase fluctuation, right, and the phases are equally spaced. You could have one of these 8 possible phases in the representation depending on the input sequence. For example, I could associate 0 0 0 here with this phase and this some other binary sequence with this phase. And of course that allocation is done usually by following the gray code philosophy with which we are quite familiar already. These are other examples just to show that we have an infinite choice here in designing constellation, right? There are a lot of variations possible. I can have in 8-level QAM in quite a different way. This is yet another way of designing a QAM system in which I have both amplitude and phase variations possible. Some kind of a regular grid, not necessarily the square grid that I had to start with, right? Here what I have got in this what I call 8 cross QAM, you will find that I have a 4-level QAM of this kind and another 4-level QAM with a different amplitude, which is some kind of crossing this. There is some kind of a crossing relationship between these two. Now these two are perpendicular of 45-degree shifted versions of each other, right? 45 degrees rotated versions of each other. This constellation, the outer constellation and the inner constellation, you can think of as crossing each other, right? So we call it a 8 cross.
Amplitude for all of them.
If I have same amplitude, I get back to PSK.
No, even if we assume that the phase is not uniformly distributed.
Yeah, it may not be. In this case, it is not uniformly distributed. In general, in any general QAM modulation scheme, the phase will not be uniformly distributed. Even the amplitude may not be uniformly distributed in some cases. For example, you can see here, right? You have an infinite choice here. It's up to us to choose a constellation to represent our given number of bits that we want to encode or use for modulation at a time. Okay? How do these things all fall within the class of band limited modulations? Because it is understood or it is implied that each of these points will be using either a common pulse shape with the same bandwidth, or maybe at best we can use different pulse shapes all satisfying the Nyquist criterion or the required bandwidth constraint. Of course, usually one uses a common pulse shape. There are situations when more than one pulse shape may be employed, but most of the time we use a common pulse shape to represent any of these points. Okay? The only attributes that differ are the resultant amplitude and phase of the carrier that goes in that pulse. Or of course, so the overall modulated waveform that comes out depends on not only this amplitude phase combination but also on the pulse shape that you use to describe it, which is assumed to be same. Any questions so far about these constellations and the concept of in general quadrature amplitude modulation? Sometimes these kinds of things are also known by the name of amplitude phase shift keying. In general is QAM systems, APK, right? It stands for amplitude phase shift keying. Okay. And they are confusing. What is confusing?
Names.
But they all imply the same thing, right? You can see each of these names makes sense because in these schemes both amplitude and from one representation to another representation both amplitude and phase are being varied, whereas in a pure PSK only phase is being varied, just to distinguish these from the pure PSK kind of modulations, right? But the most common name today is QAM. So if you remember that, it's fine, right? Now when I have this choice of modulations available, you can see that I can design a constellation in any particular manner that might fascinate me, right? But is there some pattern behind these designs, or should we consider some parameters when we are designing these constellations, right? If so, what are these parameters? We like to look at those. So I'll just first give you a few definitions and then we'll come to this point. Let me first define average energy per symbol of the signal constellation. You have a given signal constellation, right? Let's say this constellation, you have 8 symbols here corresponding to possibly 3-bit sequences, right? 8 symbols here. What is the average energy per symbol associated with this constellation? What is the average energy per symbol associated with this constellation? Because different symbols have different energies. So first thing I want to define is the concept of an average energy. So we will define this to be E sub C, which is obviously the average of the sum of the energies of all the symbols. Okay. Now as you can appreciate, this energy for individual symbols will essentially depend on the amplitude of individual symbols, right? Or the distance of the symbol from the origin, right? Which you can think of this as the sum of the real component and the sum of the square of the real and imaginary components. So if I define the real components of the mth symbol or the mth point in the constellation as C sub mr, then C sub mr square plus C sub mi square, which represents an imaginary component. This defines the average energy per symbol for a given constellation, right? If you compute this value, where C sub m is C sub mr, the real component, plus j times C sub m I, right?
So
this
means every symbol occurs with equal probability.
Okay, yes, you are right. This definition of average implies that. Right?
Occurrence of each.
That is, we are assuming every symbol to be occurring with same probability, which again would be true if every bit occurs with same probability independently of every other bit, right? Which will be true. So yes, this assumption is implied in this definition. You're quite right. Thanks. Similarly, we can define average energy per bit as this is a very important parameter. Finally, the parameter which is most important is average energy per bit. It's we will denote it usually by E sub B. It's a fairly standard notation, and this will be E sub C divided by log m to the base 2, which you can also call 1 by k or EC upon k, where k is this number, right? Repeat something. What is that? What do you want me to repeat? This definition of average energy per bit is basically, this is the average energy per symbol. Each symbol represents how many bits? Log m bits, log m to the base 2, right? Or k bits, right? Therefore, average energy per bit is EC upon k. This is as far as the energy definitions are concerned. The next parameter that is of interest is very important performance parameter of the constellation. It's called the minimum distance. On a signal constellation, and I think by the very term you know what it means. It denotes the smallest distance between any 2 points on the constellation, right? Smallest Euclidean distance between any pair of distinct points. Right? On the signal constellation. We can write a mathematical expression for it. D sub min is the minimum value of, suppose I have 2 points represented by C sub m and C sub m prime, alright, then their corresponding, the distance will be, you take the component along the real axis, square it up, take the difference and square it up, plus similarly for the imaginary part, alright, and square root of that. Minimum of this value for all possible combination of the indices m and m prime, right? So minimum over all m and m prime which are not the same. Okay, so that's a formal definition of the minimum distance on the constellation. Make sense? Now, this is a very important parameter of a signal constellation, but unfortunately this parameter alone will not suffice, because I can have 2 signal constellations which are perhaps identical in shape but have different domain by simply spacing out one constellation more than the other. That is, one constellation may have more power than the other, but that's a power advantage, that's not a constellation advantage, right? I can increase the D sub min of 2 constellations which are identical in shape but are different from each other in the sense that one has points which are spaced out more than the other. They are otherwise identical in shape, right? So I can increase the minimum distance by simply pumping in more power in the system. By spacing them out, what am I doing? How am I spacing them out? By putting in more power in the system, right? So this alone therefore is not a good measure of how good a constellation is, right? Because we must normalize it with respect to something which will otherwise make them similar, right? So to obtain a proper figure of merit for a signal constellation, we define what is called rho min. So now we come to the figure of merit, which will tell us how good or how not so good a signal constellation is in a particular sense. I'll talk about that sense in a few minutes, and we'll define it as D min. Yes, you're quite right, we have to normalize it with something, and the most reasonable thing to normalize it with is E sub C, average energy per symbol, or E sub B for that matter, average energy per bit, right? Just to give you an idea of, so we'll call this rho sub min as normalized minimum distance. Alright. Since basically it is minimum distance which has been normalized by the average bit energy, we will call it normalized minimum distance. Just to give you a feel for what kind of values we will have for this figure of merit, let me consider the value of rho min square for some typical modulation schemes. Can you make a guess for its maximum value? Just a blind guess.
2 for the QAM.
Maximum possible value for this normalized minimum distance for any constellation.
So 1
by
I am
So
getting somebody saying 1, somebody saying 2. 2. Good. A lot of you are very close to it. In fact, it is the right answer. It is in fact equal to 2. And can you give me the constellations for which it will be equal to 2?
QPSK.
PSK and QPSK are examples. Binary PSK is also I'm including this in the general discussion, although strictly speaking there is binary and not emery for PSK and QPSK. And it can be seen, you can convince yourself that this value is going to be less than 2 for all other constellations. Now, why is this important, rho min? Why do we call it a figure of merit for the constellation? Yes, that is true. Ultimately, in a digital communication system, the final performance measure is our probability of error for a given system, right? And here we are talking about the contribution of the constellation design in determining the probability of error, right? Now, it turns out that if you look at the P sub E or the error probability in a Gaussian noise situation, then it depends on the signal constellation design. Specifically, it depends on the signal constellation structure, this probability, this error probability, essentially through this parameter, right? The detailed constellation structure itself is not that significant as this parameter is, right? So the error probability is largely determined for a given signal constellation structure by this property of that signal constellation structure, right? That is, if this value is large, you will have a smaller error probability. If this value is small, you will have a higher error probability. So essentially the property of the signal constellation for the purposes of error probability calculation is largely through this parameter rho sub min. So this error probability depends on the signal constellation structure essentially through this parameter, through rho sub min. So this is a useful measure by which you can compare different signal constellations that you may like to look at. Okay? Essentially what you are saying is, if constellations are well designed, they will be such that any 2 points which are close together will have a large minimum distance, right? With reference to Varun, this disturbs me a lot, you are talking. If you have something to say, I will really prefer that you say it to me, and through me we can all discuss it together. But if you constantly keep talking to each other, it upsets my presentation. Please.
So this so is it like independent of the nature of the roadway, like with regard to the amplitude difference or the phase difference?
Yes, sir. So phase difference should be important, sir.
Yes, if you have any questions, you're most welcome to ask me. Yeah, actually we look at this later when we talk about demodulation. Error probability, talking about error probability at this point in detail will not be of much significance unless we know how we are demodulating the signals, because ultimately the final error probability depends on both how you are modulating and how you are demodulating, right? So when we take up that issue in detail, we'll discuss and come back to this point. At the moment, just keep this as a point of information in mind, right? That ultimately the most important parameter of a signal constellation which determines its overall performance in Gaussian noise. Mind you, in other situations this conclusion may not be correct, but in just Gaussian noise alone, this is the most important parameter, the normalized minimum distance. Okay, but we'll come back to possibly this question again when we discuss the error probability calculation after we have discussed how we are going to demodulate these things.
Also, Gaussian noise?
Why Gaussian noise is a very easy answer, which I'm sure you have dealt with in your first course, because most of the time the kind of noise that we encounter in communication systems can be modeled as Gaussian noise.
No, but why is it not applicable to other kind of things?
To other kind of things means?
Other distributions of noise.
Yes.
That's what I meant.
It will be very difficult for me. There is a nice answer for that, but it will be difficult for me to take it up here. Okay. For Gaussian noise, you have many very nice properties, and this is one of them, right? The fact that it is Gaussian makes life very simple for us. In fact, that's also one of the reasons why you use Gaussian as a model, sometimes when it is not even valid, which is of course wrong. Okay, let me just therefore complete the discussion by first saying something reasonably trivial and obvious. The mapping of bits or bit sequences to these points in the constellation we all understand by now, right? Essentially a group of k bits will be taken, so input data stream will be segmented into k bit segments, k bit words. So first you will divide the incoming bit sequence into k bit segments, and we will call this data words, these segments, right? We have said this a number of times. The lth data word, let's call it a sub l, right? The lth data word will be assigned to a point, one of the points on the constellation. Let's call that point a sub l, right? So lth data word assigned to this is a point on the constellation. Which will have a real component plus an imaginary component, right? So basically this represents what? A complex amplitude of the pulse that you are going to transmit, right? This lth point or a sub l value represents a complex amplitude of the pulse that you are finally going to transmit, of course with a carrier, right? So in fact this represents the amplitude and phase. Complex amplitude means it represents the amplitude of the carrier and the phase of the carrier when we talk of complex amplitude. So in general the overall complex signal that you are dealing with is going to be transmitted signal, is going to be sequence of these with the pulse shape ST, L going from, let's say, minus to plus infinity, right? This is your transmitted waveform where these ALs essentially govern the complex amplitudes of the transmitted pulse, right? That is what we call QAM mathematically, right?
Sir, like in MSK we are divided into even bits and odd bits, same data stream. Can we do that type of thing here?
One can have. I did say that when we were discussing orthogonal signaling scheme last time, I did mention to you that one can have Emery MSK kind of signals, but I didn't want to discuss them here, right? because it will become too detailed a discussion for which we don't have time. You can read about it yourself. But at the moment we are just doing a general QAM discussion. Alright. So this is the another way of looking at QAM mathematically, and in this typically this pulse ST that you will use will satisfy your, what kind of pulse shape you are going to use? Nyquist criteria. So ST to satisfy Nyquist criteria. Right? Which of course kind of implies that this pulse shape that we are talking about is not necessarily the pulse shape at the transmitter alone, right? It's really going to be the pulse shape, overall pulse shape that will result from starting from the transmission pulse shape to the channel impulse response to the receiver filter, match filter or whatever. It's a combined pulse shape that we are talking about. That is what we require, should satisfy the Nyquist criterion, and not just the transmitted pulse alone, right? Because what we finally want to make sure is that at the decision instance there is no intersymbol interference, right? In a band limited channel, that is how we go about designing our pulse shapes. This is just to recapitulate for you what we discussed under the Nyquist criteria. The final real transmitted waveform, what will be the nature of that? That is just a complex representation. What we have got here is just a complex representation, right? The final real transmitted waveform would be, let's call it CT.
The carrier we have not introduced.
That's right. So far I have not introduced the carrier, right? This is just some basic pulse shape. Therefore this is really a baseband representation of your passband signaling, right? Your final CT would be, you use that signal to modulate the carrier and take the real part of that. Take it. So it's the real part of this multiplying e to the power j2 pi FOT or FCT, whatever. Which now, because we have taken our let me go through a little bit of, so this will be real part of C bar T into cosine 2 pi FOT, right, minus imaginary part of C bar T into sine 2 pi F naught. This is the quadrature that we are finally transmitting, right, which we can represent in terms of data by just going through it further. Simplification. This in turn, what is real part of C bar T? Where C bar T is this, right? It's a real part of this. Now ST is a real pulse shape, right? In general, I should say in general, most of the time ST is going to be a real pulse shape. In general, I could have a complex pulse shape also with a real and real component and a imaginary component. But for my present discussion, let's assume that the pulse shape itself is real in nature. When do we have a complex pulse shape? When can we possibly have a complex pulse shape? Okay, we go into that issue separately. At the moment, let's restrict ourselves. Just think about it. We'll just restrict ourselves to the situation where ST is real, so that we can take this to be essentially dictated by whether the real part of AL and the imaginary part of AL, right? So it will be real part of. I think I can directly write that, right? Sigma ALR cosine. Sorry, I should have written something else.
SP minus
I better do it fresh. A sub LR ST minus LT cosine 2 pi F naught T minus A sub Li ST minus LT sine 2 pi F naught T. So that is the final transmitted waveform on the channel for a real pulse ST. Now finally, I would like to finish this discussion by this more or less completes our discussion by just mentioning to you the fact that this signal design in a two-dimensional space that we have discussed so far, right? The signal constellation for Emery passband modulations is actually a fairly important topic in itself, and one can even think of higher dimensional spaces, signal spaces. This is a two-dimensional signal space. Basically two-dimensional because we are using the quadrature carriers as our basic carriers, right? Basic signals. But in general, one can think of higher dimensional abstract signal spaces in which to carry out digital modulation signal design, right? So there is a whole subject of signal space approach to signal design, digital modulations, to designing digital modulations. Which will help us in the two-dimensional case, it will help us to design a good constellation, and this kind of a theory will also help us to possibly give us digital modulations in higher dimensional spaces which I am not going to at the moment. But basically the approach consists of first defining a space of functions which you will permit or which you will use in your modulations, in your communication system. A space of functions means a space of signals which will have some properties. Basically it will be a set of waveforms, and then you will be having a concept of, each waveform will be represented by a point in this signal space, and there will be the concept of distance, and essentially the design requirement will be such: design a point, a set of constellations in this space so that this normalized minimum distance or equivalent of normalized minimum distance is as large as possible, right? So of course that subject is outside our scope and we will not really go into it, but one has to do that kind of an exercise to achieve or design good modulation schemes. The job of the modulator is very simple. Once you design a signal constellation, a modulator is essentially a rule to map incoming data bits onto one of these points, right? That is all a modulator has to do. But a modulator designer has to design what set of points to choose and how to choose them. Okay? I think this is where we will stop this discussion.